Now that we've revisited resistors in series and parallel, we're going to look at capacitors in series and parallel combinations. They work in a similar way, but with some key differences. So while resistors in series simply add the resistances to get the equivalent, and for resistors in parallel, you take 1 over each resistance and add those up to get 1 over the equivalent resistance. For capacitors, it's going to be, in fact, the other way round. So let's start by looking at capacitors in parallel. So we have 3 capacitors here in parallel, and we're going to connect a voltage V across each one of them. You can see that each has that same V voltage. They have capacitances C1, C2, and C3 as shown. We want to know what single capacitance would be equivalent to this combination. Now we know that C equals Q over V for a capacitor. So we can say that C1 equals Q1 over V, C2 equals Q2 over V, and C3 equals Q3 over V. If we are to replace the 3 by a single capacitor, its charge, Q, must be the sum of the charges of the 3. And if we rearrange the capacitor equation, we get Q equals CV. In that case, we get Q equals C1 times V plus C2 times V plus C3 times V equals C1 plus C2 plus C3, all in brackets, times V. That means the equivalent capacitance is just the sum of the capacitance of each capacitor in parallel. You can think of those plates side by side as being just the same thing as one plate with 3 times the area, so 3 times the capacitance. So this is the rule for capacitors in parallel. What about in series? In series, the charge on each capacitor will be equal. To see that, think about one of the segments with the red dotted line around it. That segment is isolated from the rest of the circuit, so its net charge is 0. So the minus Q at one end must balance out the plus Q at the other end. Each of these internal segments cancels each other out in a similar way. So each capacitor in series has the same charge Q. The other thing we can see is that the voltages add up to the supply voltage. So V1 equals Q over C1, V2 equals Q over C2, and V3 equals Q over C3. We know from Kirchhoff's voltage law that V equals V1 plus V2 plus V3 equals Q, which is the constant, times 1 over C1 plus 1 over C2 plus 1 over C3, and that must equal Q over the equivalent capacitance. And so that leads us to the equation for the equivalent capacitance for a series combination. 1 over CQ equals 1 over C1 plus 1 over C2 plus 1 over C3 plus, and so on and so on. So you see, it's just the opposite of the case for resistors. This makes combinations of capacitors quite easy to work out. So we'll have a go now.